everyone. This is a video on dot products. We've been talking about vectors. On this one, we are going to be multiplying two vectors together. This is called the dot product. And we're going to be using dot product properties to discuss whether it is a scalar or a vector, finding its magnitude, and determining if it's orthogonal, parallel, or neither. We'll also talk about finding the angle between vectors. So let's get started. So these, once again, are vectors, and vectors can be multiplied using a dot product. This is a vector in component form. Both of them are written in component form, which means that if I put those vectors, represented by here, at their terminal end at 0, or initial end, and their terminal end would be at the point 2, -3, and the other one would be at 1, 3. Now, dot product is really easy to do. What we're going to do is we will multiply the x values together, so 2 times 1, and then we're going to add together the y values of the components multiplied together. So -3 times 3, that's going to be 2 minus 9, which is -7. Now, we've gone from vector in component form to scalar. A dot product is a scalar. We're going to end up with a single number. Here are a list of properties of the dot product, all right? And it's a lot of notation, but it shouldn't be anything that you're not familiar with. So this idea of that is magnitude. That's the magnitude of the vector u. And so we have, and the dot, u dot v, is the dot product, which we did on the previous screen. So if you take the dot product of 0, it's still going to be 0. If the dot product is 0, then that means those two vectors are orthogonal, or they are at right angles to each other. If you take the square of the magnitude of v, it equals the dot product. And then a is a scalar, so if you multiply a scalar times the dot product, it comes out to be the same if you take the scalar times one of the values, one of the vectors, before you take the dot product. And this is also a transitive rule. So I really like this screen because it talks about what do the vectors look like if you take the dot product. So here are my two vectors, A, B, right? And they are both a length. If I take the dot product, they're going to be a positive value, right? Same for these two. These two are parallel, right? They're parallel, so when you take the dot product, it'll be greater than 0. These are not parallel, but they're going in the same direction. That would make their dot product also positive. On this one, you have A and B going in opposite directions of each other, or in different directions, working against them. Their dot product will be negative. Also here, B is going in one direction, A is going in completely the opposite direction. Again, the dot product will be negative. But if the dot product is 0, you've got orthogonal. You have a right angle. And so this gives you a really good synopsis of what you're looking for. And remember that A dot B is a scalar. So you're comparing a number to a number. So I added this screen because I wanted to show you some of the theory behind dot products. We talk about the notation, and the notation can be scary unless you know what it is. So when you're talking about an angle between two vectors, right? If I had those vectors A and B, this would be the angle theta. Then the cosine of theta would be the dot product of the vectors divided by the dot product of the magnitudes of those vectors. And so notice that by doing all of this, you can find another way to find the angle in between, which we did with law of sines and law of cosines. All right. So once again, two vectors at right angles to each other, their dot product is 0 because they are orthogonal. That's just another word. Another word that they use to describe two lines that are perpendicular to each other is they're called normal lines. So orthogonal, normal, and perpendicular are talking about the same thing. Okay? So when we say vectors are orthogonal, lines are perpendicular, and lines and curves are normal. So that's an important distinction. Vectors are orthogonal, lines are normal. So I wrote this again up here. I'm not exactly sure why I did that, but bear with me. Talking about orthogonal means that they're perpendicular. So if you had two vectors and you wanted to know if they were orthogonal, parallel, or neither, and once again, most vectors are going to be neither. But occasionally you will run across vectors that are at right angles to each other, and that's an important property to know that. The other thing that's important to know is that what is a parallel vector? What does that mean when vectors are parallel? Well, it means that they're going in the same direction, but they may not be the same magnitude. In fact, on a component, in component form, that would mean that they would be in the same place, actually, right? So if I had this vector and I wanted one that was parallel to it, right, they would have the same direction, but possibly not the same magnitude, right? These are the same vector, just in a different place. If I moved this one back on top, it would sit exactly on top. But what if I had one that looked like this? Same direction, smaller magnitude, right? I could take this vector and multiply it by a number and get the same magnitude as this one, right? Because they're in the same direction. So that's what this is meaning here. That if they're parallel, they're going in the same direction, and we're finding k, which would tell me what the magnitude of the vector, like their difference in magnitude. So, for instance, if I had the vector 2, 3 in component form, and I multiplied it through by 2, then the vector 4, 6 would be parallel. These two vectors would be parallel to each other. All right, and I could find out what k was, but I could say 2k equals 4, right, because k was 2, that's what I multiplied it times, and then 3k equals 6, and k is 2. So since I multiplied both the x and the y's by the same magnitude, by the same scalar, 2, then those two vectors are parallel to each other. This is important because the question is, how can we tell if vectors are orthogonal, parallel, or neither? Voila, here's the example, right? So are these vectors orthogonal, parallel, or neither? Right? So the first thing you want to check, because it's the easiest really, is orthogonal. So I'm going to check to see if they are orthogonal. And to do that, I have to look at its dot product, right? So I'm seeing if u dot v is equal to 0. That's my question. So I'm going to take the negative 12 times 1/2, and then I'm going to add to it 30 times negative 5/4, right? And so this is going to get me negative 6 plus, now if they're orthogonal, what does this have to be? Right, it has to be 6. And so I'm looking at this here, and this is, don't take a 2, that's 15. That's like not even close, right? Negative 65. So these are not orthogonal. I don't even care what the scalar is. If it's not 0, I'm done. This needed to be 6, and it's not. All right, so let's check to see if it is parallel. Parallel, all right? So parallel, I'm looking for k, right? U, k equals v, right? So I'm looking for k. So I'm going to say negative 12k, I'm just staying in the same order, is 1/2, right? So I'm going to divide, and k would be negative 1 over 24. All right, and then the other would be 30k, and I could go the other way, and that would make it a little easier, but what the heck. All right, I'm still looking for a negative number. So this will be times 1 over 30, right? So k is equal to, then this goes in 6 times, so this is negative 1 over 24. Well, so for some strange reason, one of these vectors got multiplied by negative 1 over 24 to get the other vector. These two vectors are parallel, right? So what happens if the k's are wrong, or they're not the same? Well, then it's just neither. It's not orthogonal, it's not parallel, therefore it has to be neither. And that's how that works. So I hope you took good notes. Think about this stuff. Think about the vectors and how they are set up and what it means to be orthogonal or normal. Because these words don't go away. We're going to continue to use them and even on into calculus. So I will see you in class.